Thank you, Michael. Thank you. Now, I was told to ask, is this too loud? You can hear me so far. Good. Okay. I thought it might be useful to have a really introductory set of lectures about the way, at least that I came to study and work with intertwining, and that comes from probability, so there are a lot of experts here, and these lectures aren't for the experts; they are for being friendly for the rest of you. One thing is the lectures are based on two papers, and one paper, so references, paper with David Aldous and me, and it's called Shuffling Cards and Stopping Times. And this is in the American Math Monthly, so it's friendly and I hope understandable, and a good place to start if you haven't seen this kind of thing before. And then there's a paper with Jim Phil and Phil, and it's called something like Strong Stationary Duality. I don't know the exact title, Duality. And that's not so friendly. And on the other hand, I'll try to make it accessible to you by giving you lots of examples and spelling out things. But really, I'm going to talk through examples that are all written down there. So if there's something I say and you want to see it as better or clearer mathematically, I really do suggest that you take a look at those papers. You can find them on your phone now. And okay, so throughout, I'm going to have X, a discrete state space. I usually think of it as finite, but it could be countable. But it's a state space, and I have K. XY Markov chain that is bigger than or equal to 0, summation K XY summed in Y is 1, and so that's a transition matrix of a Markov chain. I'll always assume that this is ergodic, that is, that it's connected, the state space is connected and aperiodic, assumed ergodic. It has a stationary distribution. I'll use this notation throughout. Pi of x bigger than 0, summation pi of x equals 1, and of course summation pi of x k of xy is equal to pi of y. Here I'm summing in x is a stationary distribution, and often I'll have a starting state, pi naught, the chance that the chain starts out, its starting distribution, pi naught of x is the start. And I'll write x naught, x1, x2, and I'll call that x. For the process generated by K, and I assume you all know that's a Markov chain, and under these kinds of conditions, certainly KL of XY converges to pi of y as L goes to infinity. If you run the Markov chain a long time, it converges to its stationary distribution, the fundamental theorem of Markov chains. And one question is about how fast. And as a default, we'll talk about other distances soon, but the distance from k to pi after L steps is the maximum over A in x of KL of x A minus pi of A. As a math question, given the starting state, here I started it deterministically at x, and the question is, given epsilon bigger than 0, how large L, so that the distance of k started at x to L minus pi is less than epsilon. Okay, so that's a motivating question for the examples in this lecture. And in the course of studying this over many years, a technique came up, which is the method of strong stationary times. And I want to begin with the first example of a strong stationary time, which led to all of the stuff I've done about it. And I thought many of you may know this or even teach it to your own students, but here it comes from me. So here's an example of this setup, which is top to random. And I'll write this down as math in a second, but the state space is all n factorial arrangements of a deck of cards, and for me n is 52, and I mean that. I don't care about it, and I actually care about 52 high Lewis. And the Markov chain is the following. The deck starts out in order, and you take the top card off, and you poke it in at random, and you just keep doing that. You just keep poking the cards in at random. And it's obvious intuitively that if you do that a long time, the deck gets all mixed up. And it's a question, how many pokes does it take to mix up the cards? Yeah, that's a typical example. So as math, so x is equal to Sn, all the permutation group, all permutations. The chance of going from one permutation to another is equal to, I'm allowed to take the top card off and put it back on top, which leaves it, it's equal to 1 over n if y is equal to what happens if I take the top card off and put it in position j, then j goes to j minus 1, goes to j minus 2, goes to 1, and card 1 goes to j. So if y is equal to j minus 1 down to 1 times x, so this is the usual way of writing a permutation as cycles, right? I hope that's familiar or clear. That is, that's what happens if you take the top card off and put it at j. So if y differs from x by a cycle, then and zero otherwise. So that's the Markov chain. Of course, the stationary distribution is uniform and factorial, and the way a theorem looks in this subject, typical answer is if am I using L? Yeah. If L is equal to n log n, and whenever I write log, they're base E. The log means log base E, okay? Plus C. So if you go n log n plus c steps, then the distance starting from any place, from any x, after L steps to stationarity is less than or equal to e to the minus c. So first of all, that's something I like to do, namely no big O, no BS, right? E to the minus c, right? It's different than what other people do, but that's their problem and yours in these lectures, because I keep track of constants. And this is sharp. There's a matching lower bound, but I'm not going to be emphasizing that. Sharp, S-H-A-R-P. That is so, when n is 52, log n is about 4.5, and 52 times 4.5 is, I don't know, 200 and something, right? Something like that. So it takes, 250 pokes or something like that. You have to say, what epsilon is, and then this tells you what to do. Okay, so that's what a theorem looks like in my part of the world, and the proof, and if you haven't seen this, good, I'm happy to introduce it to you, and if not, well, sorry for doing it again. I'm going to write down the proof, but let me say it in the air, and then I'll write it down, okay? So there's my deck of cards. Here it is, right? It's deck of cards. There's some card, it starts out in order. There's some card on the bottom. I'm going to call it the ace of spades, okay? If you like, call it card labeled 1. I don't know. But there's some card on the bottom when you start, right? And I'm poking the cards in, right? Now, eventually, some card goes underneath the ace of spades. What's the chance of that happening? It's 1 over n. There are n cards. There's one place for it to go, right? So the chance that the top card, that a card goes underneath the ace of spades at the beginning is 1 over n. And so it's a geometric random variable with parameter 1 over n. So it takes order n steps, n pokes, in order for a card to go underneath the original bottom card. Okay, that's elementary. I'm going to keep going. So there's some card, whatever it is, underneath the ace of spades. And now I keep poking the cards in. And eventually a second card goes underneath the ace of spades. Yeah? And here's an idea. Suppose it happened at move 200. And I say, hey, I just put the second card underneath the ace of spades. The two cards underneath the ace of spades are equally likely to be high-low as low-high. Right? Because I'm putting cards in at random. Okay, and how long does that take? Well, there are two places for a card to go underneath the ace of spades, so it's geometric with parameter 2 over n, and so it takes n over 2 steps. And now a third card goes underneath the ace of spades. It gets inserted at random, waiting time t3, and these are random, and if I take some card and I put it in at random, the 6 possible orders are all equally likely at that time. Right? That's actually believable. It's even true. Okay, so the ace of spades is slowly moving up. It either stays where it is, because I put a card in above it, or it moves up. Right? And look at what happens the first time the ace of spades comes to the top. By induction, the n-1 factorial arrangements are equally likely. And if I take the top card off and I put it in at random, it's random. Right? That's the first strong stationary time. So let's try to write that down. These are all stopping times. If you want me to define stopping time, ask me. But let T1, so proof, let T1 be equal to first time a card is inserted below the bottom card. Okay. So T1 has a geometric distribution, 1 over n. That means the probability that T1 is equal to J is equal to, well, what's it equal to? It's equal to 1 minus 1 over n times, no, it's the other way around. It's equal to 1 over n times 1 minus 1 over n to the j minus 1. So this is 1 less than or equal to j less than infinity. That's the geometric distribution. Let T2 be equal to the first time bigger than T1 such that a card is inserted below the ace of spades, the original bottom card, and T2 is geometric with parameter 2 over n. Just there are 2 places to insert it, and keep going, and let Tn be the first time the ace of spades is on top and inserted. And so that takes time 1, right? The ace of spades is on top and then inserted. It takes time 1. So that Tn goes as geometric with parameter 1. And the time the whole thing takes, let T be equal to T1 plus T2 plus Tn. That's the first time the ace of spades is inserted. And these TIs are independent. TIs are independent of each other. And what we argued was that let me do one more. What we argued is that if xj is the arrangement, is the state of the deck at time j, then xt, the state of the deck when the ace of spades is inserted, the probability that xt is equal to any arrangement of the deck, even given t is equal to little j, is equal to 1 over n factorial. So this is important. This is the strong and strong stationary times. And think about it yourself. That is, suppose that, you were watching me, but you weren't seeing where cards were inserted, but you were listening to me. And if I said, after, well, the first time that can happen is, it takes 52 pokes. But, if I tell you the TIs, even given that information, all arrangements are equally likely. So even knowing when I stop, and so this T, this stopping time, is a strong stationary time, strong uniform time. I'll define it more generally, strong uniform time. And what it means is that the process stopped at time t factorial. The process stopped at time t is uniform even given the stopping time. And we're going to show in a second, we show that the distance of the chain after L steps, starting any place to its stationary distribution, is less than or equal to the probability that t is bigger than L. That's a basic inequality that we'll prove in a second. And so we've reduced the problem of bounding the rate of convergence of this Markov chain to understanding the sum of independent geometric random variables. And, well, you know, if you took an elementary probability course, you know, this is the sum of independent geometric random variables. You can calculate its mean, you can calculate its standard deviation, and you could say how likely it is to be where, but there's a nicer argument. Let's give that argument. So we have to bound the tail of this stopping time. And so note, T has the same law, same distribution as the first cover time of balls dropped at random. This is the coupon collector's problem at random into n boxes. So let me try to explain that. Suppose I had n empty boxes, and each time I'm picking a ball, picking a box at random and putting a ball in. How long does it take the first box to get occupied? Well, right away. Right? How long does it take the second box to get occupied? Well, the ball has to not go in that first box, right? So it's geometric. How long does it, suppose all the boxes are occupied but one, how long does it take that last box to be occupied? It's a geometric random variable with parameter 1 over n, right? And so this t has, it's just these same geometrics but written backwards. This t has the same distribution as the classical problem. It's called the coupon collector's problem. And so we know that the probability that t is bigger than L, that all the boxes haven't been covered after L steps, is equal to the probability of the union of I equals 1 to n, where it depends on L, but I is equal to box I is uncovered. No ball dropped in box I, right? After L balls have dropped in. Well, that's this by a union bound. That's less than or equal to n times the probability of the first box is uncovered, and obviously, if you're dropping balls in, that's equal to n times 1 minus 1 over n to the L. So we have proved that, modulo this fact, that the distance of the chain after L steps to stationarity is less than or equal to n times 1 minus 1 over n to the L. And then, okay, I used 1 minus x is less than or equal to e to the minus x. And if you set L to be, n log n plus c, you'll see the right-hand side is that. But you know, if you care about numbers, you can just calculate that. So that's an example of a strong stationary time. And just think about it for a second. What's nice about the argument is, well, it's pure thought. You don't have to do anything almost. Right? You can just see the randomness building up, right? The bottom 2 cards, bottom 3 cards. You can see the randomness building up, and then at the end, it's random. Right? So that it's pleasing in the sense that you can see why it's true if you see it that way. And so can I help anybody with, I'm going to fill this in and define some things a little bit more carefully, but anybody want help with that argument? It's an argument I do for high school students, so you won't understand it. Right? Many of you probably know it, but can I help anybody with any part of this argument? It'll help everybody if you ask a question. No, I mean, it's not, I don't want to embarrass anybody. That's true, it's not sharp. I didn't say it was sharp. I mean, it's sharp up to constant. Well, I mean, it's not sharp. It is sharp. N log n plus Cn is sharp, but I mean this, right? So Laurent is making the point that you could sharpen it the tiniest little bit. Instead of looking at the original bottom card, look at the card second from the bottom. Okay, there's the deck in order. Say card 1, card 2, card 3, card n on top. So look at keep poking the cards in. Look at the first time the card second from the bottom comes to the top. Okay, the same argument works. You know, the relative order, even though the ace of spades, you know, starts at the bottom, but when the card goes underneath it, when the card goes underneath the second card from the bottom, it's equally likely to go above or below, and the randomness builds up. And that is sharp. That's true. But so
the sharpness because of the total variation, and here it's in separation.
It's true.
Yeah, but there is a 2 between the two.
So, I see what you mean. Right. I see what you mean. So, it's true. There's a 2. Yes, it's true. It's true. So, sharp means order of magnitude, right? Up to a factor of 2. Thank you. You're right. Guilty as charged. Yeah. But I hope everybody, despite that, so I didn't talk about lower bounds, but anyway, I did prove this theorem. Right? So, I'm not, but it's, by sharp I mean, okay, there's a reasonable constant such that it's, if you go a little less than n log n plus c, its distance is far. So let me bring in what Laurent was talking about and try to define things a little bit. Okay. Thank you, Laurent. That's no lying allowed, especially not when you're going at this pace. Good. So go back to generality and let me define things a little more carefully. So back to x k pi. General state space, Markov chain, stationary distribution, and stopping time. T, which is a function from infinite sequences, x to the infinity, such that anyway, I'm not going to define stopping time unless somebody wants me to. I'm happy to do it, but a stopping time T is a strong stationary time. If the probability that x sub t is equal to x, given that t is equal to something little t, is equal to pi of x for all t, 0, 1, 2, etc. And another way of putting that is that equivalently, the process stopped at time t is independent of t. That's the same statement. And equivalently, and this will be useful, the probability that xt is equal to little x, given that probability that xl is equal to x, given that t happened before or at time L is equal to pi of x. That is, once t happens, the thing is random, and then after it's stationary, it stays stationary. So these are all equivalent, and that's the definition of a strong stationary time. And so it'll be useful to introduce a different distance. And so definition. In this context, the separation, sep n, is equal to the, I allow it to depend on the starting state, is equal to the maximum of over y of 1 minus the chance that after n steps, starting at x, you're at y, divided by pi of y. Okay, so as n goes to infinity, of course, this goes to pi of y, and so this goes to 1, and that goes to 0, and this is the worst case of that. That's called the separation distance, and you can observe, so it's important not to put absolute values in there. It's just what we naturally would do. Anybody would don't put absolute values in there. Okay, that's a different distance. This, because it's 1 minus something, it's bigger than 0. So 0 is less than or equal to sep. N is less than or equal to 1. That's certainly true. And sep n is equal to 1. If this sum y, which can't be reached after n steps, right? That is there's some y which you can't get to after n steps. So it means there's some y such that k n of x y is equal to 0. And sep n is equal to 0 if k n of xy is equal to pi of y. That could happen. I mean, anyway, that's separation. And what do I want to tell you about it? There are a lot of things to say about it. Here's a lemma. Well, what's my lemma? Sorry, which lemma am I doing? I wrote them down. Lemma. If t is a strong stationary time for k pi, then sep L is less than or equal to probability that t is bigger than L. Okay, so the bound that I was using before actually works for this separation distance, and the proof these are all easy. The proof is write down 1 minus k x y to the L over pi of y. Right, that's this thing I've got to get my hands on. Well, that's less than or equal to 1 minus the probability that after L steps, the process after L steps, given that it started at x, is equal to y, and that t happened before time L over pi of y. Now, why is that? Well, that's this. There's the pi of y. And then I added something which makes that smaller. And since there's minus in front of it, it makes it bigger. Right? So that inequality is elementary. But by the definition of strong stationary times, this is equal to 1 minus the probability that t is less than or equal to L, that by our definition of strong time, and that's equal to the probability that t is greater than L. So that's the inequality that I'm using, and we will prove that for every k and pi, there exists a strong stationary time t such that sep L is equal to the probability that t is bigger than L for all L. So there always is a strong stationary time which achieves this bound. So it's not only an inequality, it's an equality, and it holds for all L. And we'll prove that in due course. And the last thing to say in these little facts is the connection between strong stationary times and separation, so fact, the total variation distance minus pi, total variation, is less than or equal to sep L. And why is that true? Well, one of the many definitions, so proof, the total variation distance starting at x to pi is equal to the sum of which way to do it, KL of x, y. It's easiest if you get the direction properly. Okay, so I do it the other way. Okay, pi of y minus KL of xy over here summed over the set of y such that KL of xy is less than pi of y. Right? That's one of the many equivalent definitions of total variation distance. Well, that's equal to the sum of pi of y times 1 minus KL of xy over pi of y. And this is less than or equal to this same sum, and this is less than the separation, and this is a sum over a probability, so that's less than or equal to sep L. And so that's true for every starting state. It's true for every, anyway, that's it. That's what I had to prove. So that was the inequality I used in the middle of my example. Now this fact that there always exists a stopping time, a strong stationary time, it sounds good, but as you'll see when we write the proof down, it's completely useless. It just has nothing to do with anything. It's some existence theorem that doesn't tell you anything. The important thing for me about strong stationary times is that you can actually find them. You know, not maybe best ones, but you can actually, given a Markov chain, sometimes more than you might think, you can actually find them and bound them and prove theorems, not say it exists. So the way to understand that, I think, is to see examples. And so I want to finish this lecture by doing as many examples as there's time for. And good. Yeah?
You've defined the separation distance indexed by letter x. Is that right? That's your initial state?
Right.
You distinguish that from
Sure, it's completely different. Right? That's for children. The maximal separation is for people who don't care about the real world. The starting state can make an enormous difference in the rate of convergence of a Markov chain. Right, right. So this should have an X in it because there's an X here. Right, right. The stopping time, but if you know that, thank you. Right, that is. People got pretty lazy when they do mathematics, and they say, well, let's work in continuous time. Let's work in maximal separation. It's okay. Don't tell that to a working scientist, and especially not if it makes a difference of a factor of n. You know, if you take the example I'm about to do, but the urn-first urn, you have two urns and you each time pick a ball and move it to the other urn. If you start it with all the balls in the left-hand urn, it takes order n log n. If you start it with the two urns about balanced, it takes order n. You know, the starting state can make a big difference in rate of convergence. So, I don't know, somehow people want to be mathematicians and they've forgotten that people actually care about the answer, right? Well, okay, I still work with n equals 52. Thank you for reminding me of that. Good. Okay, so I just want to do some more examples of examples, and I'm not gonna. I don't really have time to tell you the stories, but in every one of these problems has a long story, and but this is a simple random walk. On the hypercube, C2 to the D, say, so that's the set of all, x1 up to xd, such that the set of all binary D tuples xi is contained in 0 or 1, and I'm gonna be lazy only in the interests of time. In the paper, if you look, we do the more natural walks, but so this is the, these are the vertices of a n-dimensional hypercube, 0, 0, 0, 1, 1, 1, etc. Right, the usual hypercube. And the Markov chain is pick a coordinate and change it to its opposite, except we're going to be lazy. So k of xy is equal to, what's it equal to? So it's equal to 1 over 2n if, what's it equal to? It's equal to 1/2 if x is equal to y, and it's equal to 1 over 2n if y is equal to x plus e I, 1 less than or equal to I, less than or equal to d. So n is d, sorry. So this is just pick a coordinate at random and change it to its opposite. These are binary d-tuples, and so that's you're here, you pick one of your neighbors, and you move there, or you stay where you are half the time, and so that's a Markov chain. It has a long history, an interesting history. It's also equivalent to the Ehrenfest urn. But I'm not going to tell that story. And what do I allow myself to tell you about it? Well, first of all, theorem. What is the theorem? So the stationary distribution is uniform. Pi of x is equal to 1 over 2 to the d. If you march around the hypercube, all the points get, you wind up at a random point. And theorem, if L is equal to d log to the base 2 of d plus c, that's what comes out of this argument, then the distance of KL starting any place, it doesn't matter where you start, at x, it's a random walk on a group, minus pi is less than or equal to e to the minus c. And we're going to prove this by strong stationarity, proof, by coordinate checking. And so let me explain that. So you start out with a binary vector of length d, which has all coordinates 0. Okay, and now in my random walk, I'm each time picking a coordinate at random and changing it to its opposite, or leaving it alone with. Okay, and I do that with probability of half each. So when I pick a coordinate, it's random, right? Because I've replaced it by 0 or 1 with probability of half. If the coordinate was a 1, and if I leave it alone, it's a 1, and if I add 1 to it, it's also it changes to 0. So when in this lazy walk, when I hit a coordinate, it's random, and so let t be the first time you've hit every coordinate. When you hit in this walk a coordinate, check it, and let t be the first time all are checked. And that's a strong stationary time. And you can see that once you've checked the coordinate, it's random. And once a coordinate's random, it stays random. I mean, it's a random walk. It preserves that. It's a random walk on a product chain. So you can speed that up a little bit. The following speeds it up by a factor of 2. Suppose I pick a coordinate and then I'm flipping a fair coin, and half the time I do nothing, and half the time I change it to its opposite. When you decide to do nothing, pick another coordinate at random, including that one, and check it. That doesn't change the fact that you've got a strong stationary time, and it speeds up the mixing time by a factor of 2. And but this isn't an optimal argument. It's still off by a factor of, well, that's okay. That faster one is okay. So you can again see the randomness building up as you hit coordinates. You're making them random. So the next argument is more substantial. It's work I became well known for about riffle shuffling. So example, riffle shuffling. So here my state space is Sn, X is Sn, all in factorial permutations. And the measure I'm going to be analyzing is this measure, the measure that people use when they shuffle. You cut the cards about in half and you go like that. Right? Of course, you have to make math out of that. So let's make math out of that. Cut off C cards about half with probability in choose C over 2 to the n. That is cut off according to the binomial distribution, the bell-shaped curve, and now you've got your 2 packets, this is your left hand, this is your right hand. If this has A cards and this has B cards, so I've cut the cards, I'm now dropping them with my thumbs. The chance that you drop the next from left is A over A plus B. So let's just say that in the air for a second. So suppose I cut them exactly in half. So I have 26 in each half. So half the time I drop a card from the left half. Now the chance I drop the second card from the left half is 25 over 51. Right? And then you just keep dropping them each time according to that dynamic. So that completely specifies a way of shuffling cards. Right? And there are a lot of things to say about it. I don't have time to say them, but I did write a book about it, and with Jason Fullman, The Mathematics of Shuffling Cards. It's a good model for the way real people shuffle real cards. It's not a good model for the way I shuffle cards. I shuffle en Vegas dealers. They shuffle almost perfectly. But shuffling perfectly is a lousy way of shuffling. If you shuffle perfectly 8 times, the cards come back where they started. Right? Shuffling neatly is a poor way of shuffling. This is provably, it's the maximum entropy measure supported by shuffles. It's the most random way of shuffling. And so if you like, you could say, so let Q of pi be the chance of pi after one shuffle. And you can write that down, but I'm not going to right now. But you can write down this, you can write down, I erased my mechanism. And then let, K of xy be the chance of going from x to y is Q of y x inverse. And this is a measure on the permutation group, and make it into a kernel that way. And so we want to study repeated shuffles, and what comes out of this strong stationary time is this theorem. If L is equal to 2 log to the base 2 of n over c, that's the way it goes, then the distance of k L minus pi, and I'll keep with total variation, is less than or equal to, let's see, I never write it that way, and I did carefully write it down, so I might as well carefully write it down. It's 1 minus e to the minus c squared over 2. Sorry if that's hard to parse. But so if c is small, this is close to 0, and that's close to then that's close to 1, and difference is close to 0. So if you shuffle a little bit more than 2 log to the base 2 of n times, actually the separation is small. And the reason for presenting this is because of the argument, because of the stopping time argument. So again, this is a complicated realistic Markov chain, and we have to make a stopping time, and there's a nice way of doing it. Which has some legs. It works in hundreds of other examples. So proof. So the first thing is work with inverse shuffles. So work with inverse shuffles. See, is that what I want to do? Yeah, inverse shuffles. That is, so riffle shuffles, you cut the cards and you go like that. Inverse shuffles, you take some cards out and put them on top. Right? You just do the inverse permutation. So what is an inverse, these are the Gilbert-Shannon-Reed's measure. What is an inverse shuffle? Here's a deck of cards. Flip a fair coin for each card. Okay. Take all of the heads, take them out, and put them on top. That's exactly the inverse of this drop sequentially measures. So you have to check that, but it's an elementary check. Is that okay with everybody? Everybody understand at least the idea that, inverse, and the rate of convergence of inverse shuffles to the stationary distribution is the same as the rate of convergence of forward shuffles. And so I'm going to work with inverse shuffles, and now I'm going to do the following. Where's my, okay. Label each card before you start. The deck starts out in order with an infinite binary tuple. IID, a half binary tuple. So plus, minus, 0, 0, 0, 1, 1. So each card, on the back of each card, you flip a fair coin infinitely often, okay? And you write that down on the card, or you think about it conceptually that way, okay? Well, so each card has an infinite binary label. And now what you do, the deck starts out in order, right? Look at the first column. That's some zeros and ones. Take all of the zeros, take all of the cards which have their first coordinate 0, take them out and put them on top. Okay, so as far as the deck is concerned, you did an inverse shuffle, right? Just take out all the... And now, take all of the cards, look at the second column. Each card has a binary label. Look at the second column. The second column is, again, an infinite collection, or 52 binary tuples, binary indicators. Take all of the cards which have 0 in the second column, and of course they're independent, put those on top. Now what did I just do? Well, all of the cards which begin 0, 0 are on top, because that's what I'm doing. All of the cards which are, and you have to get it straight, but it'll be straight if you think about it slowly and carefully for a minute. All of the cards which I'm going to say are 0, 1 are next. All of the cards which are 1, 0 are next. And all of the cards which begin 1, 1 are on the bottom. And maybe it's the reverse of the middle too. So you keep doing that. And what you're doing is sorting the cards. Right? If you keep doing that, the third column, all of the cards that start 0, 0, 0 are on top. And you're doing reverse lexicographic sorting on the binary n tuples. Okay, so use column I to dictate the ith shuffle. And let T be the smallest L, so that the first, there are n of these, the first L bits are distinct. So, of course, eventually, these are independent coin tosses. They'll come in L when all of these binary L tuples are distinct. Yes, of course, with probability 1. Let T be the first time that happens. So at that time, the binary L tuples are sorted. But the binary L tuples, there'll be some card that had all zeros on it actually, but the smallest card. So at time t, the cards are sorted, but the labels go on cards randomly. So you could have written the infinite binary tuples on pieces of paper, put them at random, and then glued them on the cards randomly. The card which has the lowest label in lexicographic order, it can be any card. and the card with the next lowest label can be any card. So at time t, the deck is in random order. So you have to think about that for a second, but really it is very close to the surface. So this is a strong stationary time. And so if you want to see that written out carefully, and I'll end with this, so I see the time is over. And so now I've reduced the problem of bounding the distance to stationarity to the birthday problem. That is, I have, what's the chance that it takes bigger than L shuffles? Well, that's the same as the chance that if I drop n balls into 2 to the L boxes, that there's at least one ball in the same box. So the probability that T is bigger than L is equal to 1 minus the product from I equals 1 to L, I guess, of 1 minus I over 2 to the, no, let me get that right. There's no reason to lie about it, since it's easy to do, and it's just, okay, okay, everything I'm doing is a little wrong, but not just a little wrong. It's I. This is just the birthday problem, I equals 1 to n minus 1. That is, if there are L things, you have 2 to the L possible patterns, and you're dropping n balls into those 2 to the n boxes, and you want the birthday problem to fail. And so that's equal. And then you can do the elementary asymptotics and do that in this domain. Okay, so that's just another example of a strong stationary time. So to say there are, 100 examples. There are lots and lots there are families of examples. So people have been able to find strong stationary times in a lot of different problems. And I'm very interested in the examples. I'm very pleased that we can find these kinds of pure thought arguments. There's almost no work, no Fourier analysis, no group theory, nothing. Right? You're just thinking. Just probability. So that's very pleasing when you can find such an argument. And then I got tired of proving the same theorem again and again and again. So we made with Jim Phil this notion of strong stationary duality to unify these arguments. And I will tell you about that. So just to review, one sentence of review. So what I told you about, we got started, Markov chains, and then I gave you an example of a strong stationary time, top to random, and then we defined strong stationary time. We defined separation. We showed that separation is an upper bound for total variation, and then I did the hypercube as an example, and I did card shuffling as an example. The next lecture, and I am going to stop. The next lecture, a little bit out of order, I'm going to do cutoff and birth and death chains. So there's applications of the machine that we're going to build. The machine's a little abstract, and so I'm going to save that to lecture 3, the abstract notion of duality and intertwining. I know there are a lot of people interested in that, but I think it's important to see its applications. Okay, that's my attempt at an introduction. Thank you.